तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Right, we were looking at Lorentz transformations. In particular, I said I would discuss the transformation properties of the electromagnetic fields themselves. Let us first write the Lorentz transformations in a comfortable or convenient fashion. For instance, if you look at a transformation where x prime is x minus vt over square root 1 minus v squared over c squared, t prime is t minus xv over c squared over the square root, z prime equal to z. We have in mind something where a frame, I kept labeling it in this direction, actually I should have done it properly. Here is x, here is y going into the board, and here is z, and this frame is moving along at speed v, so that you have x prime, y prime, z prime. I had this x coming out of the board and moving in the y direction, so the earlier figure. This is the right way to do this. This is s and this is s prime, and these are the Lorentz transformation equations. Then recall that we wrote this down in compact notation as x prime mu equal to lambda mu nu x nu, and this matrix lambda of coefficients was what gave you your told you what the Lorentz transformation was like. And if you recall, in this particular instance, this lambda matrix was of the form gamma minus gamma v over c minus gamma v over c and gamma, and then there were zeros everywhere else. In this fashion, where gamma was equal to 1 over 1 minus v squared over c squared to the power of half. Okay. Now of course you know this implies the relativistic addition of velocities. Law of velocities is that velocities don't just add up linearly, but you know that if you have a frame, a frame s prime moving with speed v1 say, and then a frame s double prime moving with speed v2 with respect to s prime, then you know the law of addition of velocities for velocities in the same direction is v1 plus v2 over 1 plus v1 v2 over c squared. This is the law of addition of velocities, and that is well known, okay, provided the two velocities are in the same direction, of course. Okay. Now of course we have been talking in terms of v over c, so this is really v over c is v1 over c, v2 over c, and v1 v2 over c squared. This suggests very strongly that the correct variable to look at is not v or even v over c, but rather something where that becomes a linear law of addition of velocities. And what does this v do? After all, this v can go all the way from 0, from minus c to plus c if it is a single component. Okay. Now therefore v over c goes from minus 1 to plus 1, and what variable, what mapping from x to some function of x takes you in a monotonic way, in a one-to-one way between minus 1 and plus 1? Tan hyperbolic x runs from minus 1 to plus 1, and for x sufficiently small it is actually linear, it is essentially x. So it looks like the right variable to describe, to use, is really not v but tan hyperbolic v over c, okay. And as v goes from minus c to plus c, this goes from minus 1 to plus 1, it is a bounded quantity. So let us put u equal to this guy here, and then of course it is a trivial matter to verify that gamma is 1 minus tan hyperbolic squared, and of course if you use this trigonometric identity, it says cos hyperbolic squared minus sin hyperbolic squared is 1, then immediately this implies that gamma is equal to cos hyperbolic q. Okay. And of course then v over c itself is tan hyper, so we have, sorry, we should write v over c equal to tan hyperbolic q, or u equal to tan hyperbolic inverse v over c. Thank you, that is the transformation. And this immediately tells you that gamma v over c is sin hyperbolic q. So that gives us a very simple way of writing the Lorentz transformation equation. It simply says replace this by cos hyperbolic q sin hyperbolic q with a minus sin hyperbolic q and cos u. That almost starts looking like a rotation, except in the case of the rotation matrix you had something like cos alpha minus sin alpha minus sin alpha cos alpha, it was orthogonal. This matrix is pseudo orthogonal because remember that the orthogonality condition it has to obey is lambda g lambda transpose equal to g, where g was the metric tensor. So this is a very convenient representation, and this immediately implies, by the way, that u equal to u1 plus u2. If I define tan hyperbolic v1 over c as u1 and similarly for v2, this immediately implies u is u1 plus u2. So Newton was almost right, Newton, Galileo, etc. Velocities do not add up, tan hyperbolic v over c's they add up if they are in the same direction. And of course for sufficiently small values of v over c, so if I plot here u equal to plot here tan hyperbolic, trying to see how to write this, tan hyperbolic q versus u, then of course this quantity goes in this fashion here, and here it is linear, approximately linear out there. That is the non-relativistic region. For v much smaller than c, this quantity is essentially linear. Otherwise you see that this saturates on both sides and it adds up. This quantity here u equal to tan hyperbolic v over c is the rapidity and the relativistic law of addition of velocities, for velocities in the same direction, say that the rapidities add up, not the velocities, but it is these quantities. Tan hyperbolic inverse v over c is what adds up, and that is the discovery, that is special relativity. We could have started with this law and then deduced backwards the Lorentz transformation equations too. Okay. So a very convenient way of writing this lambda. Of course a given lambda, a given general lambda would not be this, it would be in some arbitrary direction. And then of course if you make a boost from this frame to another frame in an arbitrary direction, the way to write that transformation matrix would be to first take this quantity, take this frame, rotate it to bring it to this, to bring one of the axes to the direction of the velocity transformation, move it there and then rotate back so that these axes are parallel. So the general transformation would be much more complicated, as you can see, but we have written down a special Lorentz transformation in which the velocity is actually of the second frame, the axes are oriented parallel to each other, and the velocity is along one of the coordinate axes, otherwise it is much more complicated to write down. Okay. I should also mention here right away that if you went to a frame S prime from S by moving along the x axis, and you went from S prime to S double prime by moving along the y axis or the z axis if you like, the result is not a boost from this frame to the frame S double prime, it is a boost and a rotation in general. So this means that the boosts themselves do not form a group, because the composition of two boosts in different directions is not an equivalent boost, is not equivalent to a single boost, but it is a boost along with a rotation. The rotations form a subgroup of the Lorentz group, because they are only they do not affect the time component at all, but only the spatial components, and they are a subgroup. SO3 is a subgroup of SO3, 1, but the boosts do not form a subgroup. Okay. That is why the Lorentz group is a fairly non-trivial group to deal with. Okay. Now that we know this, let us ask what happens to the electromagnetic field under a Lorentz transformation. Then we come back, after we deduce that, we will come back and write down what happens to a charged particle in an electromagnetic field, what is the actual equation of motion in the relativistic case. We will do that next, but first let us look at what happens to the field tensor. Recall that F mu nu was del mu a nu minus del mu a nu. Now under a Lorentz transformation given by a matrix lambda, you get F mu nu goes to F prime mu nu, and that is equal to the index mu is like a vector index, so this is lambda mu sigma, and so is the index nu, that is lambda nu rho F sigma. That is the transformation equation, because each of these indices acts like a vector index and there is a lambda matrix corresponding to it, and you have to contract over sigma and rho. But you can write this in a slightly more convenient form. You could write this as equal to lambda mu sigma F sigma rho, you can bring the F inside here, and this is contracted. This thing here is the mu sigma element of this Lorentz transformation matrix multiplied by F sigma rho, and then on the other side you have a lambda nu rho, but that unfortunately is not equal to rho nu. If it were, you could just contract, so this is lambda nu rho in this fashion. Had the rho been here and the nu been there, then you could have contracted and just written it as a product of matrices, but you have the same problem as before which we tackled. So what, yes, 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 I am saying the rule, yes, the rule of addition of velocities, this is not correct. The resultant of two velocities v1 plus v2 is not equal to v, is not equal to v, that's exactly the point. Huh? No, please let us be careful. No, I am not saying the law of addition of vectors is wrong in a given frame of reference. I am not saying that. Ordinary vector algebra will apply, of course. I am not saying that. When you add two 4 vectors, they add component by component in the usual fashion, and of course if the time components are not relevant but only the spatial components, they would add up also. The quantities that transform in a given prescribed way under Lorentz transformations are 4 vectors, not 3-dimensional vectors. So you see, when you go from one frame to another frame, the x component of this original vector, the 1 component, does not add up, is not the same as the 1 component there. When you go, even when you rotate, it changes, it mixes up with the y and z components, but when you go to another Lorentz frame, another inertial frame, it mixes up with the 0 component as well. So it is the 4 vectors that are now the quantities which add up. Now what I am saying is that when you add velocities, these are 3 velocities, right, this is dx over dt, dy over dt, etc. These components do not add up like they would under ordinary rotations, they do not behave like vectors. The 3 components of a 4 vector do not form a vector in any sense under Lorentz transformations. They would continue to be a vector under rotations, of course, in the conventional sense. So the law of addition of velocities is not valid, not the original one that you wrote anyway, because time gets mixed up, and that is why it is not valid. Okay. And now the further point was that there is something like the law of addition of velocities where the rapidities add up as long as these are in the same direction, but the moment you have different directions, then of course this is no longer true, it is much more complicated than that. That is the point. Okay. And the further complication was that boosts in different directions, when you compose two boosts, the answer is not an equivalent boost, and that is related to the fact that the velocities do not add up. Okay. Alright, so this is the rule now for the transformation, and of course it is easy to see what we should do. This f as a matrix goes to f prime. If I write these components as a matrix, it goes to f prime, which is equal to, there is a lambda here, there is an f here, and there is a lambda transpose here, because you need to bring the rho here and the nu, take the nu out. So this is the transformation law for a field tensor. Okay. And of course once you tell me what lambda is as a matrix, for instance this guy here, and you tell me what the original f is, I put this in and I compute what this f prime is, and therefore I know all the electric and magnetic field components in the new frame of reference. I am going to leave that as an exercise to you to do it in this case, namely in the case when you have a frame s prime which is moving with respect to x along the x direction with the axis oriented parallel to the original one with a speed v. So you need this lambda, and of course it happens to be equal to its own transpose. Then you put that in here and compute this and you find what f prime is. And remember that the 0, 1, 0, 2, 0, 3 components of f were minus ex over c, minus ey over c, and so on, and then the space components, the 1, 2, 1, 3 and 2, 3 components were the magnetic field components. When you do this algebra, here is the result that you get. So now suppose I have a frame S in this fashion and it is boosted to a frame S prime without a rotation, just boosted in some arbitrary direction v, along some arbitrary direction with a magnitude v. So this frame S prime is not moving along the x axis of the original thing, but in some general direction. Then the electric and magnetic fields in this frame, if I denote those by E and B, and those in this frame by E prime and B prime, these guys are related to these things by linear transformations which looks like this. The component of E along this direction of the boost, let me call it E parallel. So E parallel prime is the component of the electric field in the new frame along the direction of the boost. Okay. That happens to be equal to E parallel itself. So the electric field does not change, the component along the direction of the boost does not change. Similarly B parallel prime remains equal to B parallel, no change in the electric and magnetic fields along the direction of the boost, but the transverse components E perpendicular prime, and that is a vector, because if you have a longitudinal component here, the transverse one can be anywhere in this plane and it is a 2-dimensional vector. That quantity is gamma times E perpendicular, so it is multiplied by this gamma factor 1 over square root 1 minus v squared by c squared plus v cross b over c. I need not write b perpendicular here because v cross b parallel is 0 anyway, so I might as well just write it as b. So you see something like the Lorentz force coming out here in this case. It is not an accident, this is exactly how this transforms, and that incidentally is a reason for the Lorentz force, because it is precisely this term that acts. Similarly, B perpendicular prime is gamma times B perpendicular minus V cross E this time over C. So this is what the new magnetic field looks like. It is gamma times the original magnetic field, the transverse component, minus V cross E, and it could as well be E perpendicular here over C. So this is what comes out from this relation here. Of course if you rotate the coordinate system also, then the components of E get mixed up with each other and the components of B get mixed up with each other, but there is no of course mixing up between E and B. But what a boost does is of course convert electric fields to magnetic fields in part and vice versa, and these are the exact transformation equations. Again I leave this as an exercise to work this out, and let us go on to what happens to a particle in a charge in an electromagnetic field. Now recall that our original result was the following. We started off by saying the Lagrangian was equal to 1/2 mv squared plus E a dot v minus E phi. That was the Lagrangian which we wrote down for a charged particle in an electromagnetic field, and it was tailored in such a way that we got the Lorentz force equation. We got m dv over dt is a charge times electric field plus V cross B. Now we should now ask what happens in the relativistic case. First we should ask what is the Lagrangian for a free particle in the absence of an electric or magnetic field. For a free particle I know the momentum is going to be conserved, but I know the momentum is not a linear function of the velocity. It is mv divided by 1 minus v squared by c squared. I need to produce that. So let us write the Lagrangian down for a free particle, and this is the Lagrangian that produces it, mc squared 1 minus v squared over c squared to the power of half. Consider this Lagrangian, then I will explain where it came from. Okay. What is delta L over delta xi? This is equal to 0 because there is no dependence, a free particle, there is no dependence on the coordinates, but delta L over delta vi, this quantity is minus mc squared, and then there is a half 1 over square root 1 minus v squared over c squared, and then minus 2 vi over c squared. So this cancels, this c squared cancels, and that is equal to mvi over square root if I differentiate with respect to Vi, any of the velocity components, this is what you get. And the equation of motion, the Euler-Lagrange equation of motion says d over dt mvi over square root 1 minus v squared over c squared, this quantity is equal to 0. That is it. And you recognize what is inside there is just the component of the momentum, the ith component of the momentum. So the Lagrangian does produce the right equation of motion. So this is the free Lagrangian. Now where it comes from, you can actually deduce this from slightly more fundamental considerations, but I am not going to do that. I am more interested in writing down what happens when you have a charged particle there. But the fact is that you want this quantity L dt, this action, to be invariant, and if you write this in terms of proper time, this is the same as gamma L d tau. By proper time I mean the time that the particle sees in its rest frame, and I want this to be invariant this guy is invariant, therefore gamma L must be invariant, okay, and that tells you it must be equal to a constant, and if you choose the constant, when V goes to 0 the constant is minus mc squared, that is the gives you the correct normalization, then L becomes mc squared times 1 minus V squared over c squared to the half. I am not going to go further into this, we are not going to discuss this now. The reason is that I would like to see what happens to this when you put in a charge here and put it in an electric and magnetic field, and then see if you get the right answer, right experimental answer for this. Okay. Lagrangians at some level are always written down based on experience, trying to get the correct equation of motion in the simplest cases, okay, and after that you generalize it. So we are convinced that this Lagrangian is okay as it stands, and now I put in a charge on this particle and switch on the electric and magnetic fields. Then nothing much happens, this remains E A dot V minus E phi. We will see a little later where this comes from. What does this look like? It actually is the simplest invariant you can write down, which involves linearly the current as well as the electromagnetic potential, the A mu. It is essentially J mu A mu. Okay. Now what happens? Well, delta L by delta Vi gives you an extra term here. So this is equal to mVi over square root 1 minus V squared over C squared plus E. I should be a little careful here, but let me write this in velocity for all components. So let us write this plus EA exactly as before. But this is the momentum, canonical momentum by definition. So this is equal to P, that is always the definition of the momentum. The conjugate momentum is delta L over delta R dot here. Recall that earlier we just had this, now we have this extra quantity here. And what is the Hamiltonian? So let us settle that also. The Hamiltonian of this particle is P dot V minus L, where you must eliminate L in favor of eliminate V in favor of P. You must write everything in terms of P and R, but that is not so easy to do this time, because you can see that earlier when you had mV you could just write V equal to P minus EA over M, but now you have this factor also sitting here. So it is not that trivial, we need to work on this a little bit more and see what happens, but let us see what happens if we put this in. This is equal to P dot V, so that is mV squared over square root 1 minus, for the moment let me retain the V dependence here, P dot, so that is V plus E A dot V minus L, and that is plus mc squared 1 minus V squared by C squared to the power half minus E A dot V plus E phi, and of course this term cancels out, which is the whole reason for doing this. And therefore H minus E phi is this guy here, is equal to m over square root 1 minus V squared over C squared times V squared plus C squared minus V squared. I have added these two terms, this is mc squared and I took this factor out here, so it became 1 minus V squared over C squared, I multiplied by C squared and then the V cancels. So it is mc squared over this guy. Have I made a mistake? mistake. Okay, it looks it's all right, and this implies that h minus E phi whole squared is equal to P minus EA whole squared, then multiply by C squared times this plus m squared C4. If I use this quantity, I have mv squared and then I add the square of that plus m squared c squared, the v squared cancels out. Okay. So the whole idea is to eliminate this quantity here. When you do that by squaring, then you get a 1 over 1 minus v squared by c squared, and if you have a v squared on top, you want to cancel that, and you do that by adding the c squared. So this term you add, and I fix the dimensions by putting the c squared here. So this is the relation which replaces the free particle relation. The free particle relation, you recall, was E squared is c squared p squared plus m squared c4, and all that has happened when you go to put in a charged particle is that h goes to h minus E phi, p goes to p minus Ea, but phi and a are the components of a 4 vector, h and p are the components of a 4 vector. So it is evident that all that has happened is that p mu goes to p mu minus E. So switching on the electromagnetic field just changes the definition of the 4 momentum, the canonical 4 momentum. It subtracts a E a mu, that is all it does, okay. And you have exactly the same relation as before. What about the equation of motion? Notice now that the canonical momentum, this guy here is fairly messy, it is a messy function of this as well as that, but what about the equation of motion? Well, we are almost there, because that down, we know the equation of motion says, the Hamiltonian we have, now the equation of motion says d over dt delta L over delta V is equal to delta L over delta R, component by component, and the L is sitting here. All that happened was the changing in the momentum because of this term, this extra factor here, the definition of the momentum, the velocity dependence got a little more complicated here. Everything else remained exactly the same as before. Delta L over delta R, the R dependence is going to come from the R dependence of the vector potential and the scalar potential exactly as before, and all the manipulations we did earlier would still go through, there would be no change at all. The only difference would be this quantity here, this derivative. So the next few steps would be identical to what was before, and the result is exactly what we got before, which is d over dt, but now mv over square root 1 minus v squared over c squared, this quantity here, this is equal to E times the electric field plus V cross P. All this business about the total derivative with respect to time of A and so on, all that is exactly as before, all the manipulations are exactly as before, and this is the equation of motion. This is the momentum, mechanical part of the momentum, not the canonical momentum. It is the, if you like, the kinetic part of the momentum, but it has got this extra term here. This is the exact equation of motion. The same Lorentz force, the same everything as before, but it is not m dv over dt, this. But we have to deal with this, and we would like to get an equation for the acceleration itself. That is the whole point, to see what kind of equation you get. That becomes a little trickier, but let us do it. So this says, first let us move this m out, so it is this in this fashion. Then it says dv over dt 1 over the square root, and then I differentiate this, so it is equal to minus 1/2, there is a v sticking out here, when I differentiate this quantity it is 1 minus v squared over c squared to the power 3/2 there, and then I have to differentiate the v here, so this is equal to minus 2v over c squared. I am sure I am going to make mistakes here, dv over dt multiplied. So let us get rid of the, make this plus sign, get rid of the 2 here, and that is it. This is equal to e over m e plus b cross b side, and let us multiply through by this guy, the square root. So this becomes just this factor here, and then this is equal to e over m square root 1 minus v squared over c squared times that. Let us move this term to the right hand side, so that is equal to minus v dv over dt, and then there is a v vector there, v over c squared, and the whole thing is divided by 1 minus v squared by c squared. So I move this out, that is dv over dt. That is not very helpful because you still have this term sitting here, the dv over dt, so it is not very helpful, but notice the following. Notice that if I write I need to do this in a slightly better way. I need to do this more efficiently. If I take this equation and dot it with v on both sides, then I get v dot dv over dt equal to e over m square root 1 minus v squared over c squared v dot e, yeah, and then this term is 0, and I get a v squared here. There seems to be an extra v sitting somewhere. Alright, okay, minus v squared over c squared, we go boldly where no man has gone before. So v squared v dv over dt over 1 minus v squared by c squared. I dot it with v and I write that as v squared, and I retain this v dv over dt, and there is a 1 over c squared there. But I know that this can be written as v dot dv over dt, now that is the crucial point, right. For any vector v dv over dt is the same as v dot dv over dt, because each of them is equal to 1/2 d over dt of v squared. So that is the basic trick. Now once you do that, then we are in good shape, because it says v dot dv over dt equal to v dv over dt no, this multiplied by 1 plus v squared over c squared over 1 minus v squared over c squared. I bring this to this side, is that correct now? This is equal to E over m square root 1 minus V squared over C squared V dot E. And of course this thing here reduces now to 1 minus V squared over C squared, and the V squared over C squared cancels on top. So that is it. And this is V dV over dt, right. So we put that back here. So I am going to substitute for V dV over dt over this fellow here. I am going to substitute this. I am going to substitute this equation for it. So the only factor that remains, this is a common thing, and the only thing that remains is this whole portion goes away, and there is an E over m square root which comes out, and there is a V over C squared V dot E. So this is minus V over C squared V dot E. That is the exact equation of motion. Okay. So you see it is the basic identity was this, you had to use this is equal to, I use that fact and then I get this equation. So this is the exact equation of motion which replaces the original equation in the non-relativistic case. Now you see that when V over C is negligible, then this goes away, this term goes away, and you are back to the original Lorentz force. This is the equation for the acceleration of a charged particle. Okay. And now the rest follows. You can go on from here and find out what it does. I don't want to introduce, I don't have time to introduce things like the retarded potential and so on and so forth that it sees, but physically you can see very simply that the electric and magnetic fields are closely linked to each other, they are related to each other extremely intimately, they really are the same field. And when you switch on, when you couple it with matter, then all you do is this replacement P mu to P mu minus A mu. That is equivalent to saying that the interaction Lagrangian between matter and the electromagnetic field is minimal, it is of the form J mu A mu multiplied by the charge. This is all that is being said. This coupling is sufficient to produce whatever you need. Okay. Now this is the beginning of the relativistic kinematics of charged particles in electric and magnetic fields, and the extra term here notice is not a trivial term, because this function of V is not trivial, it is not a linear function, nor is this. So it leads to a large number of effects, relativistic effects. Okay. So this is all I wanted to say about relativistic electrodynamics. Let me say a few words about the Lorentz group itself as a final statement. I mentioned that the special Lorentz group, the group of transformations we are talking about is SO3, 1, which is the set of boosts, the set of rotations, they are all homogeneous transformations. Okay. Now the question you could ask is, what about translations, what about moving the origin of space time both in space as well as time, and of course you can do that, and the laws of physics are invariant under this group, not just under the Lorentz group itself, and that group is the translation group in 4 dimensions T4. It is the group of translations where I change x to x plus a, y to y plus b and so on, and t to t plus some t naught. Okay. That is an abelian group of transformations because you can do these things in any order, they commute. This is not an abelian group, rotations do not commute among themselves, boosts do not commute among themselves and so on, much more complicated group. There are 6 generators here. And there are 4 generators here. So together they form a 10 parameter group This 10 parameter group is called the Poincare group. Or the inhomogeneous Lorentz group. And this postulate of the principle of relativity essentially says that the laws of physics are invariant, form invariant under transformations belonging to the Poincare group. In quantum mechanics this has serious consequences. It says something about what elementary particles can do and can't do and so on, but at a classical level we could still ask how are these how is this group generated and what is the algebra of generators, what is the Lie algebra of generators. This is not altogether trivial, and the reason is as follows. Suppose I take a point x, a space time point, and I make a Lorentz transformation on it belonging to SO31. It could be a rotation, it could be a boost, it could be a combination of these guys. This goes to some lambda x. If in addition I also translate the space time origins, then this is lambda x plus a, some 4 vector a which stands for the shift in this origin of coordinates as well as in time. Okay. I do 2 of these successively. I do one first and then I do another. So I start with an x and I apply lambda 1 a1 to it, and successively after that I apply lambda 2 a2 to it, and the question is what do I get at the end. This is equivalent to applying, and this is a2 on lambda 1 x plus a1. When that is equal to, this lambda 2 is applied to that guy there. So this is equal to lambda 2 lambda 1 x plus lambda 2 a1 plus a2. It is not equal to lambda 2 lambda 1 on x plus a1 plus a2, because the first translation has the second Lorentz transformation acting on it. For instance, it could be a rotation acting on it. That tells you that the translation part and the homogeneous part and the inhomogeneous part are not decoupled from each other. This is not a simple group property, this is a group composition law, and the group composition law is not trivial, because this lambda acts on that guy, on that translation here. Therefore the Poincare group is not just the direct product of SO31 with T4, but it is SO31 with T4, and this is called the semi direct product. Okay. However, this is a subgroup of this full group here, the inhomogeneous Lorentz group, and it is an abelian subgroup. Now the moment you have an abelian subgroup, lots of good things happen. You can induce the representations of the full group using the properties of the using the fact that there is an abelian subgroup here. This is part of group theory, a theory called theory of induced transformations. I will not do that here, but I want to just motivate for you finally what happens when you go to quantum mechanics and look at this. But for that let us look at the generators of this group, this inhomogeneous group. This part has 4 generators which are called the translation generators. It is the 4 momentum in some sense. This part has 6 generators, and the generators look like this, J mu nu, whereas earlier you had J1, J2, J3 for angular momentum. Now you have 6 of them. This is antisymmetric, and you have 6 of these generators, of which the space components would be just the angular momentum part, but the others would also involve boosts. They also include the boost generators. Now together this obey a complicated algebra here. Since these guys form an abelian subgroup, the commutator algebra for these is simple, that is of course 0, and then these fellows here would form a Lie algebra here, which would be the typical Lie algebra which you have for something like a rotation group, except it is a pseudo rotation group, SO3, 1 here. I am not going to write that down, you will have a long combination of the J's, linear combination of the J's. Okay. Then the interesting thing is what happens when the J's, the commutator of the J's with the P's. and those are not 0 because of this property. I will not write this algebra down here, but now you can ask, how do I label representations of this group? And whenever you have a Lie group of this kind, you have an algebra and there are operators in this group, there are operators in this algebra, there are certain functions of the generators of this algebra with which all the generators commute, and those are called the Casimir operators. Let me give you an example from the angular momentum algebra. Remember that there you had J1, J2 equal to J3 and cyclic permutations. You had Ji, Jj equal to epsilon ijk, jk, something of this kind. But you also know that every component here Ji with j squared is 0. That is why you could label representations of this rotation group by the eigenvalues of j squared, and that is why when you have the hydrogen atom, for example, you discover that the total angular momentum is a constant of the motion, then the quantum numbers that you need, there is a principal quantum number and then there is an angular momentum quantum number, and since there is any component of the angular momentum is also a constant of the motion, you can simultaneously find eigenstates of that component, the total angular momentum and the total energy and the Hamiltonian. So that is the reason you needed 3 quantum numbers n, l and m. In exactly the same way you have to find the Casimir operators of the invariant of the inhomogeneous Lorentz group, and you would label representations of the inhomogeneous Lorentz group in terms of the eigenvalues of those Casimir operators. Okay. Now this is a more complicated algebra than that one, but it turns out that there are 2 Casimir operators here, and these Casimir operators, one of them is easy to write, it is just p mu, and if you now apply this to elementary particles whose wave functions are supposed to form what are called irreducible representations of this group, then this quantity here is proportional to some m squared c squared or something like that, and this value of m is a label. So this m, the rest mass of a particle, emerges as one of the labels of the Casimir operators. So it is an intrinsic property of that particle, of the representation. The other one, the other Casimir, is more complicated to write down. You have to introduce a combination of j's and p's, of these j's and p's, and there is a vector quantity called w, it is called the Pauli-Lubansky operator, and this guy here w mu, which involves the j's, which involves the p's and so on. This quantity is also an invariant, and the value in the rest frame of this particle of this object turns out to be proportional to m squared times, it involves s, it in fact becomes s into s plus 1 or something like that. So it involves another eigenvalue, and this is what is called the spin of the particle. So this is where the mass and spin come from, and although they have said this in a very vague way here, you can't justify it unless I do the quantum physics, quantum mechanics of it. The point I want to emphasize is the fact that the laws of physics are invariant under inhomogeneous Lorentz transformations. When you go over to quantum mechanics and look at elementary particles, for instance, it has profound implications there. So properties like the mass and the spin of a particle emerge from this requirement. So they really emerge as intrinsic properties which come out from this requirement. Other properties like charge, baryon number, other quantum numbers, they do not come out from these space-time requirements, from the space-time symmetries or anything like that. They come out as extra properties always, but these 2 properties emerge in a basic way due to Lorentz invariance, and this is the thing that I wanted to emphasize and end with. So it has very deep and very profound consequences. As we have seen throughout, electromagnetism itself is writable, understandable in a very, very simple fashion once you use the fact that it is a completely relativistically invariant theory. That was the original motivation for special relativity, and it happened to be a good accident in some sense, because light travels with the fundamental velocity. we have this entity which travels with the fundamental velocity, therefore its equations of motion are intrinsically relativistic. There is no non-relativistic approximation to the Maxwell equations, they are fully relativistic as it stands. There is no non-relativistic regime for a particle that moves with the speed of light, whereas for material particles you can go all the way from 0 speed right up to c. On the other hand, for something moving at something which has got 0 rest mass, it moves at speed c and it is fully relativistic already. You could also ask, what is the equivalent of the Schrodinger equation for photons? The answer is the Maxwell equations themselves, quantized, taken in the quantum sense. That is in fact the set of the evolution equations for the photon field. Well, that is part of quantum electrodynamics, we will not get into that here, but I hope that throughout I have been able to give you some flavor of what classical physics is like, where it has taken us and so on. Large chunks of classical physics have been left out, a large part of classical dynamics we have not handled at all. A very important portion we have neglected completely is general relativity. What happens when you have gravitational fields, we have not talked about that at all, that is another very major part of classical physics. There are innumerable other parts which we have not touched upon, but I started off by talking about mechanics in the general sense, dynamical systems, we went through Lagrangians, Hamiltonians and so on, moved slowly into what happens when you have many interacting degrees of freedom, did some statistical mechanics and thermodynamics, and finally moved into considerations of symmetry, a little bit about groups, and after that we moved into special relativity for a little bit, and then its most prime beautiful example of special relativity in operation, namely electromagnetism itself. So that has been a kind of broad overview of classical physics, partial, but I hope still I have conveyed to you some of the ideas involved in this field and left you with the anticipation of what we have ahead of us in quantum mechanics. Okay, I should stop here.